when I make it the explicit time, so it is here. So the common t that's no more here is just the ez. And then, of course, you must plus cc here. All right. So after this, we just consider the complex part. So we consider only this part. Okay. So after this, I just ignore the color. The color make me very headache. All right, just to highlight to you. So after this, you substitute this P like this into this double time derivative. Okay, when you take the double time derivative, you have minus I omega multiplied with the minus I omega. So you have the minus omega square. When you substitute here, you have minus I omega. Right? So this term, you will carry the half, right? The P, you carry the half. The P here will carry the half. The P here will carry the half. The P here, P cube here will give you the 1/8. And the E here, if you use the E like this, it will give you 1/2. So after this, you cancel the 1/2. So you left something over 4 here rather than over 8. And then why there are 3 here? So that's why using our perturbation expansion, do tell you why. Because this one, if you multiply itself 3 times, you get 1/8 for 8 terms. But there are 3 terms will carry this time. So this time dependence, because you have actually you have pz, you have p multiply with another p and multiply with the conjugate of p. So this one you multiply with its conjugate and multiply with this. So you at the end you get back this time dependence. We have done this before for the expansion for the perturbative. So the perturbative expansion will really help you to understand this p to the power of 3. So when you expand, when you substitute this to here, you will get 8 terms. So 8 terms, and then 3 of it, 3 of it will contribute, will have this part. Okay. Of course, altogether are 6 terms if you consider this CC. Am I right? Yes, right. So yes, I'm right. So let me see. 1, 2, 1, 1, 2, 1. Altogether, you have 8 terms. Yeah, right. So you have 3 terms like this. You have 3 terms which carry this factor. You have another 3 terms carry the conjugate of this factor. So that's why you have the 3 here. So remember, every term carry the half, half. This term also carry the half. Right, so altogether you have 3/4. Okay, so after this, there are typo error here. I should not have the t anymore because every term will carry this. So this term will appear here, and here, left and right. So you can cancel the exponent I omega t like this. So if you cancel the constant half and cancel this exponent I omega t, then you have this. Okay, so this is your important starting point for your holiday work. Okay, right. So is it the same as article? Yes, it is the same. It is the same, except the constant. Except this constant. So we look at how to work out this. So there is a constant m over e here. So according to this paper, nothing here. Okay. So can see the verb so at the end we can cancel it. Okay. So I think I a bit okay. So actually we have not worked out the time dependent yet, but I think it should be okay. It's very confusing. So you multiply with these blue terms first. Blue terms, and you simplify this one, you get 1, like here. This one, okay, this one and this one, we name it as gamma, like here. Instead of gamma, so we look, this is gamma. This is a kappa or n, okay. And then this one is beta prime over me square. And then this, of course, you have the e square over m, like in the paper. And then this one, beta prime over me square, it is beta. So once it is here, we name this constant. Okay, and then k kappa over m is omega naught square. So here I follow the paper correctly. Yeah. This one is later on we work out the time derivative. Okay, so when you look at this, I substitute, but I haven't worked out the time derivative yet. Okay, so the t is still here, so it's correct. The t is still here. So after we deal with the constant, so we get it the same as the paper. So with the definition, so there is a definition which is a bit different. Okay, I think it's this. So that's why I said that I'm confused. Gamma equals to gamma prime over m, but mine is this. There is an extra e here, but I think the constant should be okay. So later on, we put the time dependence into this last equation. So as I said, the double dot will work on here. You have the negative. Okay. You have the negative omega square. This one, you have the minus I omega. Okay, when you put into here, it doesn't change. Okay, omega naught t. This is omega naught square p. No change. 304 is here. So this one multiplies with the conjugate, multiply with itself. You will get things like this. Okay, so this one is this term multiplied with the conjugate. So you have its magnitude square. And of course, this is the time, with the time if something is here. So remember when we put this, just now all the half already cancelled. So this one we just consider the functional complex conjugate, I mean the complex. And after this, we just simplify. Okay, this one simplify means that you can delete all these things, all these exponent I omega. Okay, delete this. So you can get this. Okay, and then there are p over all these terms. You factor out the p. Right, so when you factor out the p, you see something like this. So this term and this term, you can rearrange to omega naught square minus omega square. So according to paper, this term is this. This term is this. And just now, the kappa OM, we already used the omega naught square. This is correct. So we have exactly the same as article at the end. So this is the equation in the equation 3. Right, we have it. Copy and paste here means that we achieve the target. All right. So we have achieved this target. Okay. So in order to use